Hi everybody, I'm going to talk about carbocation rearrangements in this video. So the most important thing to think about in terms of carbocation rearrangements is that if it can rearrange to form a lower energy product, it absolutely will do that, okay? So it's very, very difficult to stop a rearrangement from occurring if it has a chance to go to a lower energy product. So there's really two types of shifts that we're going to be looking at. The hydride shift is probably the most common. So it uses a hydride, so an H with 2 electrons. So it's basically an H taking a whole bond with it. It is the most common one. So if I have a carbocation like this, so currently it is a secondary carbocation. Okay. If I do a hydride shift, I'm going to go move that whole bond. So notice that my arrow is coming from the bond. I'm actually going to point it at the carbon there. So I'm taking the electrons and the H with the bond, making a new CH bond on my carbocation. And if we look to see what that has done, I now have 2 H's over here, but now I don't have a hydrogen on this carbon. So now my carbocation is there. Okay, so now I've got a tertiary carbocation, which is more stable. Okay, so I went downhill in energy. And all it needs to do is just push over a little bitty H, and then you get it. Okay, so the second type is a methyl shift. So we're going to be moving a methyl with the lone pairs from the bond, or with the electrons from the bond. It can also be other alkyl groups, so sometimes this is called an alkyl shift. The methyl is more common than other alkyls, but you will see alkyl groups moving in cases of kind of like specialized rings or something like that. You can see that effect as well. So in this case, we have 3 methyls over here, okay? And if we think about, if I had an H, I would just do the hydride shift, okay? Moving a hydride is easier than moving a methyl. And apart from that, if we just take a look here, if we look at what happens when we move a methyl when we did have the chance to move a hydride. So if I move this, I go from a secondary to a secondary. There was no benefit there, so we're not doing that. Okay, so it's going to be very clear whether you're doing a hydride or a methyl shift, because if you have a hydride to move, that's always going to be the one that you pick, because then you keep as much substitution in terms of carbon atoms where they are staying put. Okay, so if I have a bunch of alkyl groups, that's the only option I have to move. Okay, so if we take one of those methyls, shift that over, so now I've got 6 electrons around that carbon. So now that is my carbocation. Okay, so that's what we're looking for. Make sure that you don't do this when you should be doing a hydride. So we'll make a little note here. Okay, we're only going to be doing alkyl shifts if we don't have a hydride to move. Okay, alrighty, so let's talk about multiple rearrangements. Okay, so multiple rearrangements are more rare. They're not quite as common as single rearrangements. They are possible as long as each new product is lower in energy than the previous. okay? And what I mean by that is we'll take a look at a couple of examples and just make sure that every time we go through a rearrangement, we're ending up somewhere lower than where we started. So let's take a look at this carbocation to start. Okay, so when I first start, I've got a primary carbocation. Not good. It's really not good. So I really need to be checking out what are the things attached to that carbocation and can I move anything to make it a better carbocation. So one thing that we really want to keep in mind here is that we are looking at adjacent carbon atoms. Okay, we're not going like all the way across the molecule and then shifting something crazy distances. We're just talking about one carbon away. So if I'm looking at this carbon, I'm looking at these two carbons for possibilities for rearrangement. So we're not looking that far. So right now, if I've got a primary, I really only have this one option. But if I move one of those H's, I can get to at least a better carbocation. So let's switch that. So that's going to get me to now a secondary, and I've made a methyl on the end at this point. Okay, so now I'm at a secondary carbocation. That's better, but we still need to look and see like, okay, is this my final resting place essentially of my carbocation? So again, we look at the carbon that has the carbocation. If I go back here, I'm ending up back at my original structure. If I'm going over here, that's a possibility, and I do have an H there. So what happens if I take that one, move that over, do another hydride shift? So now I've got two H's on that carbon, and my carbocation is over here. So now I've gotten myself to a tertiary carbocation. Okay, so each of those is getting to a more stable product. So if I scooch this over so that I can have a little bit of space to draw here. All right, so if we look at the reaction coordinate diagram, so we're starting kind of up here, moving down to secondary, and then tertiary. So each of those is becoming more and more stable. So we're going this kind of pattern. Okay. Oh, goodness. It's right on the edge of my iPad. Sorry. So there we go. Okay. So each one is going down in steps. So if I take a look at an example where it won't work, so this is good. So let's pull up a similar compound here. So if I'm looking at this, I've got a secondary, but it's really tempting that I'm looking over there at that tertiary, and maybe I'll even make it more tempting and throw in a pi bond over here. Okay, so we really, really want to get over here because that's going to be a really big energy decrease. But to get there, I have to go through this. So I do my hydride shift. And I get here, and then I can do my other shift. Oops. Okay, and I get to a tertiary allylic carbocation. So I started off with a secondary, went to a secondary, and then a tertiary allylic. And that's all well and good. This step is not, okay? If there's no energy benefit right away, that's not going to happen. So if we look at the reaction coordinate diagram here, we're going to see something a little bit different where we're starting off with 2, and then getting to another 2, and then getting way down here to a tertiary allylic. Okay, so it's going to be something like this. But we're not ever going to get over that. Okay, that's going to be too high for us to be able to go from something that's the same energy. We might as well just stay where we are. Okay, so this would not happen. So each step has to be lower in energy. Okay, so we're not going to be hopping all the way down a molecule to get to a tertiary site if all of those hops are going to be similar energies. Okay, so we're only going down in energy. That's the only way to go. All right, so as always, let me know if you have any questions, and we will practice all this in class.